Every major scientific discovery begins with a question. Sometimes, however, the answer creates even more questions than the original mystery. The James Webb Space Telescope was designed to study some of the most distant objects in the universe. Its enormous segmented mirror collects faint infrared light that has traveled across space for billions of years. Webb can reveal ancient galaxies, newborn stars, massive clouds of dust, and distant worlds that were previously difficult to observe. But imagine what might happen if scientists discovered something within those observations that did not immediately fit their expectations. Not an alien spacecraft. Not a mysterious planet. Something far more subtle, a pattern hidden inside enormous quantities of astronomical data. Modern observatories generate extraordinary amounts of information. Astronomers use sophisticated computer systems and machine learning techniques to identify structures that human researchers might overlook. Most unusual patterns eventually turn out to have ordinary explanations: detector effects, calibration problems, cosmic ray contamination, or natural astrophysical processes. But suppose one pattern survived every initial test. Imagine researchers noticing unusual similarities between observations taken at completely different locations in the sky. The signals would not necessarily be evidence of an unknown civilization. Instead, they might represent an unfamiliar physical process occurring across enormous distances. One hypothetical possibility would involve gravitational lensing. Gravity can bend light. When a massive galaxy or galaxy cluster lies between Earth and a distant object, its gravity can distort and magnify the background light. Astronomers have observed this effect many times. Now imagine that a future observation revealed a lensing pattern that was unusually complicated, one that appeared to produce repeated structures around an apparently empty region. At first, scientists would probably suspect an ordinary explanation. Could there be a faint galaxy hidden there? Could dark matter be producing the gravitational effect? Could the telescope's calibration be responsible? Could multiple objects be overlapping along the same line of sight? These questions would have to be answered before anyone could claim a genuine discovery. The most intriguing possibility would be that the strange pattern represented a previously unknown configuration of matter or gravity. Scientists might then compare the observation with data from other observatories. If independent instruments detected the same structure, the mystery would become much more serious. Computational systems could search the measurements for mathematical relationships. A repeated pattern might emerge, not necessarily an intentional message, but perhaps a clue to an underlying physical process. Prime numbers would be particularly interesting because they are fundamental mathematical objects. Yet finding prime number-like patterns inside random data would not automatically prove intelligent design. Random processes can occasionally produce apparently meaningful sequences, especially when researchers search through enormous datasets. This is why scientists use statistical tests. They ask how unlikely a pattern really is and whether the same result appears when the analysis is repeated using independent datasets. Now imagine that another strange feature appeared. Photon arrival times seemed to show repeated intervals. Again, the first explanations would be mundane. Instrument timing, background radiation, processing artifacts, or periodic astrophysical sources could produce such behavior. Only after those possibilities were eliminated would researchers begin considering more exotic physics. Could spacetime itself be producing an unusual effect? Modern physics already tells us that gravity affects the passage of time and the path of light. Around extremely massive objects, these effects can become dramatic. So while a genuine, cosmic mirror, or temporal structure remains speculative, the underlying scientific questions are real. What is the true nature of spacetime? Could gravity emerge from deeper principles? Is information fundamentally connected to the structure of the universe? And how much of reality remains hidden simply because our instruments are not yet sensitive enough to detect it? These are not questions that can be answered by a single image. They require years of observations, independent verification, theoretical work, and rigorous testing. And that is what makes the mystery so compelling. Because sometimes the most exciting discovery is not an answer. It is evidence that we have found a question that science has never encountered before. The deeper humanity looks into space, the more obvious one fact becomes. The universe is stranger than our everyday experience could ever prepare us for. The James Webb Space Telescope allows astronomers to study environments that existed billions of years ago. Every distant galaxy observed by Webb is effectively a glimpse into cosmic history. But the most important discoveries may not always be the most spectacular images. Sometimes they could be hidden inside patterns that initially look like noise. Imagine astronomers identifying an unusual signal that appears in multiple observations. The pattern does not behave exactly like ordinary instrumental noise. It does not perfectly match a known star, galaxy, or transient event. Researchers would then begin the slow process of verification. They would inspect the telescope's instruments. They would repeat the observations. They would compare the results with independent observatories. They would test different data processing methods. And most importantly, they would attempt to prove themselves wrong. That is one of the foundations of science. A fascinating hypothesis is not enough. Extraordinary claims require extraordinary evidence. Suppose, after extensive testing, scientists discovered that the strange pattern was connected to an unexpected gravitational phenomenon. That would already be revolutionary. General relativity predicts that mass and energy influence the geometry of spacetime. Light follows that curved geometry, creating gravitational lensing. But what if future observations revealed a phenomenon that could not be explained by the gravitational structures currently known? Researchers might investigate whether an unusual distribution of dark matter was responsible. They might consider whether several distant objects were aligned in an unusual configuration. They could even explore whether the effect pointed toward physics beyond the standard models currently used to describe gravity and cosmology. None of these possibilities would automatically prove a parallel universe, higher dimension, cosmic intelligence, or artificial message. Those ideas belong to speculation until evidence supports them. Nevertheless, unexplained observations can become incredibly important because they force scientists to investigate the limits of existing theories. The history of physics is filled with moments when unexpected observations eventually led to major breakthroughs. That is why astronomers continue searching. Webb's observations could contribute to questions involving dark matter, dark energy, black hole formation, the earliest galaxies, and the structure of spacetime itself. Machine learning may also become increasingly important. Advanced algorithms can process enormous datasets and identify subtle correlations. But artificial intelligence does not magically transform noise into truth. Its predictions must still be tested against observations and physical theory. If an algorithm discovers an unusual pattern, scientists must determine whether the pattern is genuine or simply a consequence of the way the data were analyzed. That distinction is crucial. A computer finding something strange is the beginning of an investigation, not the conclusion. And perhaps that is where the real mystery lies. Humanity has built instruments capable of detecting light that began its journey before Earth existed in its current form. We have developed mathematics capable of describing black holes, expanding spacetime, quantum particles, and gravitational waves. Yet enormous portions of the universe remain unexplained. We still do not know the true nature of dark matter. We do not fully understand dark energy. We are still investigating how the first galaxies and supermassive black holes formed so rapidly. And we do not know whether our current description of gravity remains complete at the deepest levels of reality. The next major discovery could come from Webb, another space telescope, a gravitational wave observatory, or an experiment that has not even been invented yet. Perhaps it will confirm something scientists already suspect. Perhaps it will completely overturn an accepted idea. Or perhaps it will reveal a phenomenon that requires an entirely new explanation. For now, the universe remains an enormous scientific puzzle. The strange patterns imagined in this story are possibilities, not confirmed discoveries. But the search for genuine anomalies is real. And every time humanity looks deeper into the cosmos, we increase the possibility of finding something that changes the questions we ask. The sky is not giving us all the answers yet. It is giving us clues. And the greatest mystery may be how far those clues will eventually lead us.